started. That's working. Thank you. Good morning, everyone. So today I'm going to talk a bit about the stabilization of the advanced LIGO laser. And actually, most of the pictures and data I'm going to show are not made by myself. I've actually taken them mainly from the colleagues working at the Albert Einstein Institute in Hanover. So I'm not really the guy that built the stabilization system, but I hope that I can give you a good overview anyway. Okay, so I want to start with repeating actually the requirements we had, and I want to show you again some slides that I've already shown, which actually display where we are so far with everything I displayed. I've already shown. And then it will turn out that there are three main points left to really get to these requirements here, and that would be the beam shaping of the laser beam, the intensity stabilization, and we have to work a bit on the frequency stabilization. So let's start with that. And one requirement is that we were asked to build a laser which gives something like 180 or 200 or 165, depends on where you look, that amount of output power. And we, I think we already talked about that reason. We talked about it quite a lot, but I'm going to repeat it anyway. And the main reason why people wanted to switch from a 35-watt laser to a 180-watt laser was that the detector was limited by shot noise. So the quantum noise of that instrument consists of two components, and that's the shot noise and the radiation pressure. And if you look at these curves, which I've, it's a bit hard to see. I took a reference here. I was kind of inspired for this picture here by the Geo web page, actually. And I think it shows nicely what happens if you go from low power to high power. So these are the noise curves. And what happens at high frequencies, so above a couple of 100 hertz or so, is that you can really improve the shot noise. So that's this part, and we learned yesterday that this frequency factor here is not really what you expect from the shot noise. It's a characteristic of the instrument itself. However, at low frequencies, more laser power means that you add some thermal noise. So in this frequency regime here, if you go to this green curve here, then you would see that you do not really gain anything. You made it worse, actually. So the LIGO instrument is kind of designed that you want to have a working point somewhere close to this or the highest sensitivity, somewhere close to this point where the two contributions of these sources are equal. And actually, the curve which represents the points of the lowest noise, that's called the standard quantum limit. So I put this smiley here because I think I've already shown that we are at that point, so we were able to build these high power lasers. However, there are more requirements. For example, we want to have a linearly polarized output for various reasons. One of the reasons is that linearly polarized beams are kind of easy to handle. Other reasons are that are coating issues, issues with thermal birefringence. But we also built that. So the front end itself already delivers a linearly polarized beam. And I've shown you this birefringence compensation yesterday, and we also have the Brewster plate inside the high power oscillator, and that ensures that we have a linearly polarized output beam. These requirements I tend to put on this kind of slides. It's kind of a soft requirement. I mean, who knows what it means? Something should be easy to maintain, but I think it's more or less okay. So I don't think that we have to do much more improvements there. Another thing is that we want to have this Gaussian beam profile, and what we normally do is we don't do this m-square measurement with scanning over the beam and then say the beam has a beam quality factor of 1.2 or so. We normally do that with a primo cleaner or with some sort of primo cleaner. We scan over the eigenfrequencies of this high finesse resonator, And then we see at which frequency how much power is actually reflected and transmitted. And then we end up with these curves that I've shown before. So these are this is one free spectral range here between these two high peaks, which represent the fundamental mode. Here's a picture of the beam profile. And then all these other modes here, they actually represent other transverse modes left over, so to say. So this is a logarithmic scale, so it's not as bad as it might look like. But anyway, there are a lot of peaks, and if you sum them all up, then you would find something like 8.2% in non-DM00 modes in this case. Yes? Well, we do, but not for the final characterization of the laser. Well, of course, a beam has to be mode matched to the pre-mode cleaner. So you need a set of lenses and make it such that the fundamental mode actually fits into that cavity. I mean, if you have a fundamental mode beam, then you know the beam parameter product. So, yes, I mean, in that sense, we care about it. I mean, you need to know that because you need to know at certain positions how big your beam is, and you need to somehow be able to calculate the mode matching and how to put the lenses and so on, and which lenses to pick. We measure it, we put it somewhere in a manual or so and tell people, okay, here's the laser box and the waist of the beam is some centimeters inside and has a certain size. And then people would know, okay, let's assume it's a pure fundamental mode beam, and then they can calculate from that point on. Yeah.
Multi-dimensional modes, how do you assert that this is a multi-transverse mode operation and not a multi-Lewis-mode operation?
Well, I would still call it a single transverse mode laser. So if you look at this picture and you actually do this m² measurement, I guess a lot of people know how it works. So you actually put a camera at different positions at the beam, and then you look at the beam parameter product. So you measure the waist and then how it diverges. And if you do that measurement, then I'm pretty sure that you would end up with an m² number of something like 1.0 something probably. Is that the question, or did I miss it?
If m² parameter is nearly 1,
yeah.
And if you are getting multiple modes like this in the frequency scan of the Fabry-Perot,
yeah.
how do you ensure that they are not multi-transverse, multi-Lewis modes?
You mean like, well, actually, this is actually it's the eigenmodes of the resonator you're scanning over. So it's kind of a bit a different thing. And of course, the real number might be a bit higher because, as you can see, there is this blue curve is just a fit, and the red curve is a measurement. And yeah, there might be some peaks which make it a bit worse, of course. Yeah. Okay. Or are you talking about the?
Can I rephrase the question?
Sure.
Yeah. You said that some of these peaks represent transverse modes or residual transverse modes in the power. We just want to know whether you're sure these are only transverse modes and these are not longitudinal modes which are also being lasered.
Okay. So now, well, not really sure. I mean, it's what we call a single frequency laser. So it's kind of an injection locked system already. So I think it's not too many longitudinal modes included in that scan. I'm actually not really sure. That it might make a slight difference. So if you would have a narrower line width, then it might be that it's getting a bit better. So not 100% sure about that.
What exactly is scan to make this measurement?
You have this high finesse pre-mode cleaner that I've shown yesterday, for example, in that diagnostic breadboard. And what you do is actually you change the length of this cavity, and that changes the eigenfrequency or the resonance frequency of that thing by just changing the length. And so different modes fit into the cavity. Actually, that's the trick. Okay.
So in that sense, this will catch only those modes which
Yes, that's right. And yeah, maybe I can come back to that point later on when we come to the high power pre-mode cleaner, because it's indeed a bit of an issue. Okay, so we end up with this number. Maybe it's slightly better, maybe it's slightly worse, but if you have a 200 watt laser and you have something like 8%, so yeah, there would be something like 16 watts or so, which are in higher order modes and not really useful. That's kind of a bad thing. I mean, it's more power than you ever had in the initial LIGO laser. So no nice smiley here. For the frequency stability, we have this requirement here, 10 hertz per square root hertz at 10 hertz. And I've already shown you this graph here. So the red one is a measurement of the PSL. The blue curve is what we expect from the NPRO. So I think we can assume that whatever frequency noise comes out of the high power laser is kind of tied to the frequency noise of the NPRO. But the requirements are are way below here. So this is this point I just mentioned, 10 hertz per square root hertz at 10 hertz. At higher frequency, it's a bit more challenging. But on the other hand, at low frequencies, you have quite a difference here. It's something like 4 orders of magnitude, which you have to handle by the stabilization I'm going to show you. The amplitude stability, it's something like 2 times 10 to the minus 9 per square root hertz at 10 hertz. And actually, there are several bands for that. So that's a requirement downstream the suspended mode cleaner. So there is between the laser and the Michelson interferometer, there's a thing called suspended mode cleaner, which helps to actually clean the beam profile a bit more. And the power noise requirement at that point is this. So it's most challenging at 10 hertz, and then it's getting a bit more relaxed at higher frequencies, and at frequencies above 500 hertz, we end up with 10 to the minus 7 per square root hertz. And that's important because there are several coupling ports. Of course, if you have fluctuations in the output power of the laser, then you would see that somehow in your gravitational wave signal directly. But you also have other coupling ports, like, for example, you have this pressure fluctuations on the suspended optic. So there is a non-constant amount of photons hitting the mirrors, actually. And also you have some coupling into the control loops for various control circuits. And this is where we are again. The red curve is a measurement. The blue curve is a requirement with this really strong dip here at 10 hertz. And it's getting a bit more relaxed at higher frequencies and also at lower frequencies. So also quite a lot of work to do. And then, least but not last, there are also some requirements for the pointing, so the movement of the beam jitter, the shift, and the angular tilt of that. And I've shown this picture here when I've shown you the how it's measured with the diagnostic breadboard. And we are also slightly above the requirements, which is this black curve here. So in other words, we have to work on these 4 points a bit, and I try to give you an overview how that's done today. So the first thing is the beam shaping, so getting rid of this 8.2% of higher order modes. And that's done with a high power pre-mode cleaner. So it's kind of a similar thing as this triangular resonator, which is in the diagnostic breadboard. In this case, it's set up such that it's, maybe I show the next slide first. So it looks like that. In this case, it's a 4-mirror cavity, so the 4 mirrors are sitting here in the end. And then the beam path in that thing is kind of in this bow tie shape here. So the beam is somehow coupled into that thing at one mirror, and then it's coupled out on the other side. Yeah, that thing is, as you have seen, it's sitting in this sort of tank. It's supposed to be sealed, and the main idea behind that is that people didn't want to have any contamination on the mirrors and so on. However, there were some issues in the past with that, so the mirrors are glued to the spacer here, these 4 mirrors, and if that box is totally sealed and there is some outgassing due to the thermal load on the mirrors, then that might cause some problems. So we have seen some reflexes coming out of the incoming mirror, which is actually supposed to be not the case, and there was some sort of film found on that mirror, so we played around a bit with removing the lid and then seeing how it's getting better and worse, and I think that that issue is fixed by now. As at the diagnostic breadboard, one of the mirrors is glued to a PZT element, so that's movable, and the length of of this cavity can be changed by applying a certain voltage here. And it can be changed by about 2.5 micrometers, which kind of corresponds to 2.5 free spectral ranges. And that's used to lock this, this primo cleaner with the technique we have discussed before. Yes?
Go back to the previous transfer.
This one?
The FSR is 150 megahertz and the FWHM is roughly 0.5 megahertz. Right?
The what is about 3.5 megahertz?
FWHM is nearly 0.5 megahertz.
Okay.
That would lead to a finish of nearly 300.
I think that's not an F, it's supposed to be an H. Good point.
Whereas the finish mentioned is 124.
Yeah, I think I made a mistake here. I think it's not full width half max, it's half width half max.
Okay.
So sorry for that, yeah. I think I made a mistake in this case. Okay, yeah, these are the parameters of that thing. So the intracavity power can be calculated to be something like 8 kilowatts, free spectral range of about 150 milliwatts, and as we have just seen, the half width at half maximum is 560 kilohertz. Thanks for that comment. Okay. So now what's the task of that high power primo cleaner? So we are not using that really as a diagnostic tool. So we are not doing the same as with the primo cleaner in the diagnostic breadboard, like we are scanning over the resonance frequencies and then looking which mode fits into it. The main purpose of this thing is to keep it locked with this Pound-Ruhr-Hall scheme again, such that only the fundamental mode is transmitted and all the other higher order modes, these 8.2%, are reflected. Another issue is that we reduce the pointing sort of passively by that thing. So if you have a certain beam pointing, and you can always interpret that as a contribution to the TM01 and the TM10 mode. So that's kind of these two modes which have this little gap in the middle, and then you have two parts. And I think it's kind of easy to imagine that if you have a beam and then you have a certain beam pointing and the beam moves around, that you get a contribution to this first higher order modes. And this instrument is actually made to filter this mode, so they will be just reflected. And by that mechanism, you reduce the pointing of the system. You also have some suppression in the radio frequency range, and I think it's kind of nice how these lectures fit together. So I don't think that I want to talk too much about it, but we already talked about this program called Finesse yesterday, and I think we also talked a bit about transfer function, and I don't know, maybe we comment on that again today. I don't really know, but if you really take this Finesse program, and maybe we can do that as an exercise, that I dig out the parameters of that primo cleaner, like the path length and the curvature of the mirrors and so on, and the reflectivities, and then you guys use Finesse to calculate the transfer function of that system. Then you will see that it acts as a low pass with a certain corner frequency. So at low frequencies, that thing is actually doing nothing to the power noise, but in the radio frequency band, the noise is greatly suppressed. So yeah, maybe we can really do that as an exercise if we hook up Finesse anyway. Okay, and here's how it works. There are actually three curves. The black one is just a fundamental mode fit, and then you have this green curve, which shows the situation kind of upstream the primo-cleaner. In this case, the TM00 content was a bit better, so it's a different measurement, maybe even at a different system. But what you can see is that these really high peaks, this one, for example, or these, they're really greatly suppressed by the primo-cleaner. So the blue curve is the situation downstream the primo-cleaner, so that's what you actually use as a usable beam. And there's one peak which you cannot get rid of, and that's this TM40 mode. And the reason why it's there is not really because it's in the laser, it's because the eigenfrequency of this mode for that primo-cleaner is very, very close to the TM00. So it's a design issue that this mode cannot really be suppressed. Then here's a plot of the pointing, which is also greatly suppressed. I've shown you the red 4 curves here for shift in both directions and then tip and tilt. And if you take one of these curves and you calculate actually how much pointing suppression you have, then you would end up with a factor of about 63 from the calculations. And if you grab one of these curves, you take into account this factor of 63, then you would end up with this light blue curve here. So that's what people call the projection. And then this dark blue curves, these are the actual measurements downstream the primo-cleaner. And there's quite a difference in that region, which is, I believe, caused by electronic noise somehow. But in this region, it sort of fits. And we also meet the requirements here, apart from that region. So that looks like a huge acoustic bump. And I'm not really sure if I'm up to date with this measurement here. So it might be that that's already fixed by putting the laser into an acoustic enclosure or so. I'm not really sure about that. Yes, please. It's related to the, that's a good question. So what you use as a reference is actually a locked beam which goes through the primo-cleaner at the diagnostic breadboard. So that's what you use as your reference. So you assume that the primo-cleaner at the diagnostic breadboard is stable, and then you look at the divergence of the reflected beam for that thing. So good question. How do you compare this beams? Okay, you keep the primo-cleaner at the diagnostic breadboard locked. So you have two piezo mirrors somewhere on that breadboard, which kind of steer the beam such that you really always match to the primo-cleaner itself, and then you have also a part of the beam being reflected, and you overlap these two beams, and then you look at the interference pattern. So you actually do this differential wavefront sensing, and that then gives you an idea how the beam moves with respect to the primo-cleaner. Okay. Okay. Then I'm going to show you this measurement on the suppression of the relative power noise. So as I said, I like this expression relative power noise more than RIN. And this is a high frequency range, and as you can see, we are well below the requirements, except for this peak here at 35 megahertz. And I guess everybody can guess what causes that peak, right? Can you? My hint is that we use a Pound-Dewar-Hall locking to lock that high-power primo-cleaner. So that's actually caused by the modulation frequency, which creates a sideband. So that's exactly 35 megahertz. Well, yeah, and the filtering factor is something around 10. So that's apparently enough to bring it below the requirements here. Great. So that was already a third of the work, so to say. Now I want to comment a bit on the intensity stabilization. And I want to talk a bit about the different noise sources in laser. And the first thing we already talked a lot about is the quantum noise. So you have this effect that you you have individual photons which are kind of created, they are uncorrelated. So the only statements you can make are kind of statistical statements. And the statistics that you use for these photons with discrete energies are below the laser threshold. So if you pump that crystal and there's just some fluorescence occurring and so on, then you use the Bose-Einstein statistics, which is kind of this curve with the huge fluctuations around the mean value. The interesting part is as soon as you reach the laser threshold, you have to use the Poisson statistics. I think it should be Poissonian distribution, and that gives you a much smaller deviation around a certain mean value. So that's actually the probability to find the photons at a certain slot here. And well, these fluctuations are getting even smaller if you have more photons, so if you increase the laser power. We talked about that already a lot. So that's the quantum noise. The thing which is usually much worse is technical noise. And I just came up with a couple of points. So this is not a complete list. It's just what just came into my mind. And I think I covered quite a big portion. So you have, for example, noisy power supplies, switching power supplies, which create some noise. You have power lines, like I don't know what's in India actually, but it's usually something like 50 or 60 hertz, depending on the country where you are. So you end up with some discrete lines in the power spectrum and the higher harmonics of that. You have a low-pass behavior for the coupling between the pump light and the laser light. So that means if the pump light is kind of noisy for some reason, then you would end up with some noise in the laser output power normally. And that's getting better at higher frequencies actually, because the laser can just not follow that fast. You might have turbulences from the cooling water, so we try to prevent that by having this pump chambers designed such that you don't really directly hit the crystal. You might have acoustic noise, vibrations, resonances, and that's normally taking part somewhere in the kilohertz band, like between, I said 200 hertz up to like 10 kilohertz or so. And then you might have thermal changes in the active medium or in the pump light. So I don't think that that's really a big issue with the PSL, but that might occur in general. Then you normally have some relaxation oscillations, and that's caused by, if you want to build a laser, you need to have some population inversion at the upper laser level. So then that's depopulated by the laser process itself, and then you have to pump it up again. And so it's kind of an oscillating behavior at a certain frequency. And it's normally in this frequency range. For the NPRO, it's around a megahertz. So this relaxation oscillation is, I think it's at 1.2 megahertz or so, somewhere in that region. And we can try to manage at least some of these sources. Of course, there's not much we can do against the quantum noise, but that's anyway in the first order. It's kind of the not really the issue if you want to build a laser. For the technical noise, you can take care of at the design of the laser to make it as less noisy as possible, no vibrating parts and so on. Especially at LIGO, the laser is put into an acoustic enclosure, so that damps the noise from the environment, which might couple into the laser box. And for the relaxation oscillation, these NPROs normally come with something which is called noise eater, which is kind of a funny name. But it's basically a control loop which aims to just suppress the oscillations at exactly that frequency. Okay, so that's a curve of the requirements again that are needed for LIGO, and we are not really quite there. I've shown you that curve in the beginning where we had at 10 hertz this noise at about 10 to the minus 3 or so, somewhere here. And then it's going down, and at a kilohertz, it's somewhere in that region next to 10 to the minus 6 or so per square root hertz. And these are the requirements, and there are actually two lines, first loop, second loop, and that might already give you a clue that there are somehow two loops involved. And indeed, that's the case. So there are two loops, and they were for a long time called the inner loop and the outer loop. Maybe it's good to replace these expressions because it can cause some confusion with in-loop measurement and out-of-loop measurement, and that's a completely different thing. So, but what we call these loops is kind of shown in this little picture here. So you have the N-Pro somewhere, you have the phase modulator, the amplifier, then the injection-locked high-power oscillator, and then this high-power beam here. So you have this injection-locking loop here, which we already talked about. And then you send this high-power beam through an AOM, an acousto-optic modulator, and that can be used to diffract a part of the beam, something like 10% or so. And then if you control the voltage which drives this EOM here, then you can actually pick how much light you want to have diffracted and how much light you want to use in the really usable beam. So that kind of works as an actuator for the power stabilization. And now the big question is, how is this actuator driven? So how do we decide how much voltage we want to apply? And there are these two loops. One is right here in transmission of the primo-cleaner. So there are some. So this is this bow tie shaped primo-cleaner, and there is some light leaking out of all of the ports. And one of the ports can be used to put a photodiode here. So the light we are going to stabilize has already passed the primo-cleaner, which means that you also can get rid of effects which are caused by the primo-cleaner itself. And that's what is called the first loop, or the inner loop, if you want. And then there is a second loop, which brings the stability even further down to the requirement. So if we go back to that picture here, so the first loop is somewhere here, the second loop goes even further down. And the sensor for that is placed behind the suspended mode cleaner. So the beam is sent out of that laser room where this optical table here is placed, is sent to a suspended mode cleaner with suspended mirrors, and then to the interferometer. And the requirement I'm talking about is measured here. So you need another sensor here, which does then the rest of the work. And that's what's called the second loop. So let's first talk about the first loop. And the requirement here was that you want to have actually two photodiodes, two because you want to do an in-loop measurement and an out-of-loop measurement. And the difference is an in-loop measurement is that's kind of a thing where you actually use the diode which is also used to build the loop, which is used for the stabilization, and then you measure what's going on here. So that would give you some sort of information on how good your control loop is. An out-of-loop measurement is an independent measurement. So you put a photodiode somewhere. Well, in this case, it's also here, but you could also put a mirror here and then measure somewhere here without using that photodiode for something else. So it's kind of an independent measurement which tells you how good the work is that you've done on the laser in the end. So you want to have two of these. And then you also want to have a photodiode, a quad photodiode, which tells you how big the pointing is, because it's if you have only one photodiode and the beam is wiggling around a bit, it's kind of hard to tell whether the fluctuations that these photodiodes see are coming from real power fluctuations or if you're just moving off the center of that diode. Okay, yeah, and these two photodiodes should be, the in-loop and the out-of-loop photodiode should be sort of the same, so they should be interchangeable with the switch, and then you won't see any difference in the measurements. And that's how that thing looks like. So it's a little box which is placed next to the laser, and then the beam comes in here. It's splitted into several parts, so that's the steering mirror which goes to the quad photodiode, and the other part is then separated by another beam splitter and then sent to these two photodiodes. And the whole arrangement is made such that there's no direct backscattering. So if you have this photodiode, then and if you go to it in a perpendicular angle, you always have to be afraid that there is some backscattered light which then is bounced back to the diode itself and disturbs your measurement. So everything is kind of oriented in this 45-degree angle, and all the reflected beams are catched by these little beam blocks here, and then the whole thing is shielded in a dark box, and even the beam path from the primo-cleaner where you pick the signal to this box is shielded by some tubings to get rid of the environmental light. And it's yes, it's p-polarization.
45 degrees is not the best angle for minimizing the reflection from the. If you look at the BRDF of the gas diodes and the reflectivity versus angle, there's some medium angle at 25.
Yeah, but I think the idea was not to minimize the reflection. The reason why it's in 45 degree is more like you don't want to have a direct back reflection to the diode.
Yeah,
So, but
I don't need to go to 0 degrees, but there's some angle between 25 and 45, which is
that
reflection vanishes for some reason. It's not
that might be.
booster's angle, but it's another 20.
Actually, I'm not really sure whether that's exactly 45 degrees. To me, it looks like that. It's drawn that way. But as I've said, I've kind of taken that picture from other people. So, but it also looks like that in that photograph here. So, yeah, maybe it's not the optimum. And that's what we get. So that's the curve that we had before. And if you look at the out-of-loop photodiode of this little box, and then you look at the power noise again, you can see that it's already greatly suppressed. So it's not going down to 10 to the minus 9 here at 10 hertz, but the first loop is not intended to do that. So that's the work of the second loop. I'm pretty sure that in the meanwhile, people got rid of this peak, so that looks like some acoustic again. And the last thing I heard is that people were investigating that and trying to figure out where it comes from. And I think I've seen a measurement where this is no longer present. So I think that's some effect that people sort of fixed. Oh, and then another requirement was that you want to have a certain power fluctuations within a 12-hour period. I've shown you a graph before where it looks more like 1% power fluctuations for the free-running laser, but that were only a couple of seconds. So over a long time period, it sort of looks like that, which also fulfills the requirements. Okay, and then the rest of the work should be done by a second photodiode, and that's actually a really cool device, I must say. So I worked a bit on it in the last couple of weeks, and yeah, it's a really nice piece of electronics. So I'm going to talk about this photodiode here. And the problem with that is that you really, really want to have a high sensitivity. So you really want to go down to the quantum limit for that photodiode. So that would be the ultimate limit, which would be given by this formula here. So the quantum noise, again, would be proportional to 1 over the square root of the power, which is measured here. And that's sort of the fundamental limit for, I mean, as long as you go with traditional methods, it's kind of the fundamental limit for the measurement of the power fluctuations. However, it cannot really be reached for 2 reasons, and one reason is that you pick the light with the in-loop photodiode, so you use a part of the light for the stabilization, and that decreases the amount of photons which are available for the out-of-loop measurement. So from the perspective of the out-of-loop photodiode, you would end up with a slightly less laser power. And if you have less laser power, then this quantum noise here increases, and that's one of the reasons why with the traditional methods you cannot reach the quantum noise limit, actually. Another reason is that you pick a piece that the noise which you're trying to compensate for with this in-loop photodiode, that noise is actually imprinted on the out-of-loop measurement. So there are reasons why you can come close, but you cannot really reach that limit. So let's look a bit at this thing here. So if you look at that formula, then you would see, okay, if I want to come close to or if I want to lower the quantum noise of the measurement, then you have to go to high powers here. And if you look at this formula, then you can say, okay, I need a lot of photons, so that kind of gives you the number of photons. The other part here kind of gives you the energy of the photon. So, and that's going to be converted into electrons by some sort of photo diode. So it's converted into some sort of photocurrent. So what you want to do is you want to pick a fair amount of light for this measurement, convert it into a relatively high photocurrent, and that would bring down the quantum noise. So that's this kind of pink curve which is shown here. So you can say, okay, let's just grab something like a watt or so of the laser beam and then try to do this measurement, and that would bring down the quantum noise of the measurement itself. However, that would cause that you need a lot of photocurrent, and that cannot be done with traditional photodiodes. So normally they give you a maximum photocurrent of something like 80 milliwatts or maybe 100 milliamps or 100 milliamps or so. So you have a certain limit here. And the number LIGO was aiming for, this 10 to the minus 9, that's unfortunately sitting somewhere in this limit. So it's kind of a tricky situation, because you cannot just put a photodiode there and then apply some, I mean, you can try to apply some cooling and some low noise readout and so on, but normally the photodiodes are not capable to handle this amount of power. So not good. Yeah.
I have a silly question. Quantum noise requirement shows that one should go for higher power to reduce it. So what is the power to be included in the quantum noise calculation?
Actually, this is the
for a photodiode which is looking at the signal from the LIGO. Is it the circulating power or the power that is reaching the photodiode?
Oh, it's a power that's reaching the photodiode. So this whole setup is not placed inside the interferometer. It's outside. It's behind the.
Tremendously low when compared to the 800 kilowatts of circulating power which is to be inside.
Well, actually, I'm only talking about the requirements behind the suspended mode cleaner. I do not really know the numbers inside the Michelson, actually. Okay, there's a workaround for that, and that's, okay, if we cannot do it with one photodiode, let's grab multiple photodiodes. So people came up with this really nice design, I think. It's made such that there are, again, no direct back reflections to some optics to the photodiodes. But the main thing is that the beam is not brought to one photodiode. It's distributed by this beam splitter and these two mirrors to 4 separate photodiodes. And each one has its own low noise readout electronics. So each one is a really low noise power sensor of these. And with this method, you can actually get something like an overall photocurrent of something like 200 milliamps or so. So that should be plenty to go to the requirements. And that's how it looks like. As I said, it's a quite nice design. So you can come in here at some point. You have this beam splitter here, which is sitting in some sort of groove, and hold it with these clamps, and then the beam is bouncing around here at the mirrors. Actually, here's this filter for blocking of the reflected light is sort of missing here. And then the light is sent to these photodiodes, and you might realize that there are not 4 but 8 of these photodiodes, and the reason again is that that you also want to have an out-of-loop measurement, an independent measurement of how good you really are. So that's done with the periscope, which is sitting here, and I have a couple of more pictures of that. So here's the drawing of that thing that I've just shown. For the photodiodes, you want to remove the glass. So if you buy a photodiode, it normally comes with a protective glass that's, in the worst case, uncoated and also causes some back reflection. So that's cut off, which is kind of tricky because you have these tiny little wires here for the quad photodiode. It's really hard to see, but you have these wires going to the connections. And then this is a picture from the back. So the photodiodes are sitting in this kind of cylinder, and they are clamped to the back plate of that array. And that's a picture of this periscope. So the beam would come in here, and then there is a beam splitter here, which equally or gives, it's a 50% beam splitter, and that gives the same amount for the upper photodiodes as for the lower photodiodes. So ideally, you want to have them all the same. And one part which is critical and which is kind of the reason why these photodiodes are not just bolted down somehow, they're just clamped. One of the reasons is that one thing that you might not really think about, but what you really have to know is that these photodiodes have an imperfect surface. So they have some pattern on the perfect, some roughness on the surface, some roughness. And you really, really want to work at a point at the surface of this little photodiodes with a diameter of only 2 millimeters or something, where you have a really even surface. And the way that thing is aligned is you use a test laser. In this case, it's an NPRO with the same polarization as what you will have later in the actual system. And then you use a PZT-driven mirror, so that's a mirror which is doing this tip and tilt all the time, actually. You align it through that thing, and then you move these photodiodes around until you find really a spot where this movement of the beam on the photodiode is minimized. So you hook up some sort of spectrum analyzer, you look at the frequency which you use to modulate this mirror here, and then you try to really find a point where the fluctuations of the power that you see at this frequency at the photodiode are minimized. That's a picture of the setup. And then this setup, so again, this is the backplate of that array. So you can attach one of these XY stages, and then you can move the diode around until you think that you found the optimal point, and then you clamp that thing down and hope that that's really that's really what we call the sweet spot. Sweet because it's really sweet to not have any fluctuations caused by the photodiode itself. I think I'm gonna skip the electronics part. Or maybe I talk a bit about the signal whitening. So then you apply some sort of low noise electronics, and a common trick that people use is they use what they call signal conditioning or whitening filter. And what that means, if you have an analog signal with quite a high dynamic here, and you only have a certain amount of digital channels, so to say. So that's what this signal here, it's an analog to digital converter, then you might really lose some resolution due to the fact that you only have a certain amount of channels, so to say. So what you normally do before you do the final readout is you apply some sort of whitening filter. So it's a filter which is doing this, if you know that signal, and that whitens the signal, so you don't have this huge dynamic here again. You do the conversion then, and then you do the de-whitening filter, so it's kind of the reverse process here, and then you again have the full response for your readout. Yeah, it's just to give you an idea on what all this electronics is about. So then just in the last month, in November, that array was finally finished and assembled, and then it was ready to go into one of these HEM chambers. So we already talked about these different chambers here, HEM and BSC, and it sit in this HEM2 chamber. So the laser room is somewhere here, and there's a periscope which brings the beam out. It's going through various HEM chambers. It's moving around here, going through the suspended mode cleaner. It's coming out of the suspended mode cleaner through a Faraday. Then it moves to this power recycling mirrors, and then it goes to the into the Michelson interferometer arms. And this photodiode array is sitting in reflection of the suspended mode cleaner, as I've shown in the schematic before. So you have some sort of pickup beam behind one of the mirrors, so that's a Faraday, and behind one of the mirrors there's a slightly amount of light leaking through, and then the photodiode array is sitting here. And as you can already imagine from this picture, this chamber is pretty crowded, so I'm showing some 21st century pictures here, and that's how it looks from inside. So this sort of towers here, that's the suspensions for the input mode cleaner. So it's a really beautiful piece of mechanics, I can say, but it's kind of crowded. Everything is baked, so everything is really clean, and that's why people have to wear this bunny suits here. So it's a complete suit, you have a protection for your mouth, and you have to wear gloves. You can't touch anything else except the baked parts and so on. And then it's kind of crowded here. You have to crawl in and somehow align that photodiode array with respect to the mode cleaner, which is also an issue because that thing has to be kept locked actually during all the time. But that's the last situation I've seen. So that thing is inside. The array is here. So that again is one of these mode cleaner things. Here's the Faraday, and yeah, of course we checked for all the connections in air. So nobody knows what happens in vacuum because that hasn't been done yet, but it seems to work. So as I said, that's sort of recent work. So I don't have any data which show you how well that thing performs. But of course, it would be a bit silly to just build that thing, put it in, do the calculations, and then assume that everything is working. So of course, there was some testing with a 2-watt NPRO. And well, this graph has been published in a paper by Patrick Quay. I'm sorry, I forgot to put the reference here, but that's a paper where I actually put that graph from here. And you have this out-of-loop measurement. That's this red curve, and you can see that it's not limited by electronic noise, which is this bluish curve here, and goes all the way down to the expected quantum noise. And of course, it's below the requirement. So the most critical part was this frequency at 10 hertz here. And yeah, we are actually there, at least with a 2-watt NPRO. So I'm really excited to see what's going on with the high power laser. Rana?
This is on the tabletop. It's not in the suspended system.
Yeah. That's in an optical lab at an optical table. It's not measured in the ham chamber. So as I said, it's just a couple of weeks ago that we installed that thing. So there are no measurements yet, as far as I know.
The one in Louisiana has been running for 3 months or so.
Oh, okay. But that's not this measurement. Do you know where it is? To which level they?
It's beyond the yellow. Yeah.
Oh, that's too bad to hear. Let's see how Hanford is. I think part of the reason was that there was some problem with the alignment of that array, because yeah, maybe I comment a bit on that. So you have this moving around of the diodes, and then you clamp them down. But the beam is not perpendicular hitting this diode on purpose. So you do a slightly misalignment once you clamp this diode down. And I think that was kind of the problem, that we had this pre-alignment, and then that thing was shipped to Livingston, and the alignment was basically done. It might also have been a different spot size and so on. So it's a kind of a critical thing to pre-align this instrument. Okay, how much time do I have? 5 minutes. Okay, so let's rush through the frequency stabilization. These are the requirements. So there are several bands for the frequency stabilization. One is, for example, this what we call tidal band. And for that band, we want to have some long-term stability in the range of more than 100 seconds. So that's what people call long-term. And the requirement is comes kind of from the fact that the change in the frequency of the laser should be lower than the change in the arm length of the Michelson, which is caused by the Earth tides, so by the moving of the Earth plates caused by the moon and so on. Then there is this region which is called control band, and it's called control band because that's kind of the frequencies which are used for log acquisition at the interferometer for different purposes. So it's not really the band where the gravitational waves are measured. And the requirements for that are shown here. They're made such that the change of the frequency of the laser are lower than the change of the arm length, which is caused by seismic events like earthquakes and so on. And then the thing which I'm going to comment on is this gravitational wave band. It's from 10 hertz to 10 kilohertz. And this is how it looks like. So it's, I think I've shown that before. So at high frequencies, it's kind of critical. Low frequencies, it's a bit more relaxed. And that's where we are. As I said, we have something like 4 orders of magnitude to compensate for. And that's done with three nested loops. So there are 3 different cavities which are used as a reference for the stabilization. I'm going to comment on this one. So that's the PSL reference cavity, which brings the thing down to something like 10 to the minus 1 hertz at, I think, 100 hertz or so. Then we have the input mode cleaner, the suspended mode cleaner, which is used as a second reference, which makes it better. So that brings it down to something like 10 to the minus 4. And then, of course, we have the Michelson itself with its long arm cavities, which are used as a reference cavity, and that brings that down to 10 to the minus 7. And what we use as an actuator, we have already seen that the frequency fluctuations of the whole high power system actually follow the frequency fluctuations of the N-probe. So all we have to use as an actuator, or the main thing that we have to use as an actuator, are connected to the N-probe, and that's as a slow actuator with a huge tuning range of a couple of gigahertz or so. It's the N-probe temperature, which actually changes the length of the N-probe crystal and therefore changes the frequency. We have the N-probe PCT, the piezo element, which sort of press on the N-probe crystal and then changes the index of refraction of that thing via stress. And that can also be used as an actuator. It's much faster. So I think it's somewhere in the 100 kilohertz region bandwidth, but the tuning range is of course a bit lower. And then we have an EOM as a phase control, which works with really high bandwidth, so it's something like 500 kilohertz or so. So again, it's 3 nested loops which are used here, and I have this picture here. So again, the light is coming out of the high power stage, it's going through the Primo cleaner, and then it's leaking out of one of the mirrors again. And then and this is the reference cavity, and then we try to lock the laser frequency to this very stable reference cavity. And again, for this purpose, a Pound-Ruhr-Hall scheme is used. So there's an EOM which creates the side bands, and then the laser frequency is tuned such that it fits to the resonance frequency of this reference cavity. However, there are various other things. So the other parts, the other loops have to take into account. So the beam is sent through an AOM in a double path, and an AOM creates an acoustic wave actually, which is moving around. And if you pass through this AOM, then that causes some Doppler shift in the frequency of the laser, and that Doppler shift is of course the driving frequency for this AOM. So you go through it in a double pass, which means that the frequency of the beam which goes to the reference cavity is actually shifted by twice the Doppler frequency, twice the driving frequency of this AOM. And that's the trick how this loop coming from the suspended mode cleaner is connected to the frequency stabilization done at the reference cavity, because the driving frequency of the AOM is set by some mechanism which is connected to the measurement which is done here at this photodiode. And then there's also this tidal feedback, this very high stable loop, and that actually acts on some resistors. So this cavity here is put in a tank, and it can be heated, and then you can influence on the length of that cavity, so on the resonance frequency, by changing the temperature, and that's this third loop here. And that's how it looks like. So it's basically a fused silica spacer here with 2 highly polished mirrors. It's sitting in a tank. It's even suspended, so it's hanging here on these mounts. And as I said, that thing can be greatly heated. Okay, so I'm going to show you one of these Bode plots we were already talking about. So that's kind of the transfer function for the TTFSS. So that's one of these nice abbreviations. TTFSS stands for Tabletop Frequency Stabilization Servo. And that's what that thing does. So you can see actually you have a high gain at low frequencies, and then you have unity gain at something like 500 kilohertz, as I said. So that's how this thing is designed. And then this response goes further down here. And if you look at this lower picture here, then you can see that there's something called left, which is called phase margin. So you can easily imagine if you have a high gain, but the phase flips for some reason by 180 degrees, that would kind of a really bad thing to do, because then your actuator, your servo, is doing kind of the opposite of what it's intended to do. And the difference between this 180 degree phase flip and what you measure at unity gain, that's called the phase margin, and we have some 40 degrees or so left in this case. Okay, and again, I have only an in-loop measurement. I think the out-of-loop measurement is somewhere here, but as far as I know, people are not really sure that that's really what's going on. It might be limited by the sensing of the of this measurement itself. So the in-loop measurement kind of shows you what the servo is kind of capable to do, and at least this measurement is below the requirements, although that it doesn't help you much that I'm saying that, because it's not an out-of-loop measurement. Last slide. So that shows the overall log acquisition of the whole system. So in this upper graph here, you see what the injection locking of the high power oscillator is doing. So there's something like you turn on the lock, or you get that system into lock, and then at the same time you see what the locking of the primo cleaner is doing. It needs a bit more time, and then it's moving down here, but still it's in the region of a couple of seconds. And then the intensity stabilization is doing. It's also, of course, seeing that, and then it's working fine. And this is what the reference cavity is doing. I think it's losing log here after a couple of seconds, but then it grabs log again, and it's kind of stable here. Okay, so as a summary, I've shown you how a high power primo cleaner works as a mode filter. It reduces the pointing, and it also helps at the high frequency power noise. I've shown you these two nested loops for the intensity stabilization, and I've shown you the three nested loops for the frequency stabilization servo. I haven't shown you the final measurement, but at least the first loop of this seems to work as designed. And that's it. So that's a picture of this photodiode array again. Here you see the photodiodes from the other side. So I'm really impressed by the engineering work of this thing. Questions?
Stabilization part, both EOM and AOM are employed to get the frequency modulation.
Yes.
So what was the selection criteria whether to use a EOM or AOM?
Well, it's not both for the frequency actuation. The EOM, that's a device that gives you the sidebands that you need for the pound-Ruhr-Hall locking. So this whole thing again works like this pound-Ruhr-Hall locking. You send the beam to a cavity with the sidebands, and then you look how the sidebands beat with the carrier actually. The AOM is only made there to shift the laser frequency around, and you need that shift because you somehow need to get the other nested loops, the one coming from the suspended mode cleaner. You need to take that somehow into account. So you somehow need to add some actuator, and that's what this AOM does. So this AOM is not there to diffract a part of the beam as in the intensity stabilization. You just use it as a frequency shifter.
Immediately after the NPRO, I think I have seen both EOM and AOM.
Right.
Okay. What was the requirement for that?
Was kind of, I don't think that AOM is in use. It was in use for enhanced LIGO, but it was kind of the same actuator. So that's what this high power AOM, what the high power AOM is doing. So right now we have an AOM right behind the high power stage, which diffracts a part of the beam, and that gives you some control over the power noise actually. And the AOM inside the inside the front end, right behind the NPRO, that was in there for the same purpose, but it's no longer in use yet.
Sorry to ask you this question because already told I could not catch that. You have told about multiple photodiodes used in the intensity stabilization routine, that part. What was the aim for using multiple photodiodes?
What was the... Shall I go back to the slide maybe? Oh, that's the reason why we need multiple photodiodes.
Yes.
Okay, that's because you need a kind of a high photocurrent to get down to the required sensitivity. Because if you want to have a power stabilization which goes down to 10 to the minus 9, then you need to measure a certain amount of photons, so you need a certain photocurrent, because if you don't get this high photocurrent, then you would gain some quantum noise in the measurement itself. Unfortunately, you cannot do that with only one photodiode, because that photodiode would just be destroyed if you put too much light on it.
Thank you.
So that's the reason.
Okay, if you have no further questions, we reassemble at 11. But 5 minutes before 11, we want to have a group photograph, so please assemble there before we come.